Okay, in this video, I want to talk about chemical reactions and charges. And first, I want to tell you that whenever we have two elements that are joining each other or two elements that are combining each other, there should be some kind of force between them or something that could help them stay together. And a lot of times in physics and chemistry, we always say that the opposites attract, meaning that if the charge of something is positive and the charge of something else is negative, they will always attract each other because, again, the opposites attract, and the ones that have the same type of charge, let's say my negative and negative charge, they will always try to run away from each other. Okay, this means that every single time we have a chemical reaction, there should be some kind of charge going on between those two elements that are in the reaction, okay? Now, in general, there are a lot of different charges that we can talk about, but in this video, I just want to talk about the charges that you need to know for general chemistry, and I will give you a very good shortcut for the most important elements that you need to know for general chemistry. And if I used any drawings or anything to explain something, again, I will tell you that it's the way that I learned it, and it's basically the way of classic chemistry, and that's how a lot of people learned it. So I'm just gonna be using that for this video. Okay, the most important thing about this video and basically the way I'm writing all these down is the fact that I'm only talking about the most popular ones and the ones that you will always see in general chemistry and the charges you need to know for general chemistry. And as you can see, I only drew out the first two columns of the periodic table and basically one, two, three, four, five, six, and the six important columns on the right side of the periodic table. And I use this because when I took general chemistry in university, we basically used these a lot, and I'm pretty sure if you're taking general chemistry, you will be using this a lot. And first, I want to explain to you that why do we actually have charges, and the fact goes back to, again, the thing that I talked about at first, the fact that opposites attract, and we need to have those charges for two atoms to combine or two elements to combine. And in general, I will tell you this shortcut that every single element that you see in here, they always want to have a full shell or full outer shell or orbital. And what this means is they always want to have their outer shell full of electrons. Now, what does that mean? If we are in the first shell, 2 electrons means full shell. When we're in the second shell or the second orbital, 3, 4, 5, 6, 7, 8. 8 electrons means a full shell or full orbital, which means for all the elements that are over here, a full shell means a shell that has 8 electrons. And for all the elements that are in the left side of the periodic table, a full shell means 2 electrons in their outer shell. Now, the way I want to explain this is by drawing out every single atom for all of these. I might draw out every single one of them, or I might just draw one or two just to explain it. Now, I want to start with helium or neon. We can start with helium. Helium has a atomic number of 2, which means the number of electrons and protons are the same. And when we're trying to draw it out, helium has 2 electrons in here. As you can see, helium already has a full shell. Do you think helium would be willing to basically react with another atom or not? Well, it turns out helium is like a very lazy element. It doesn't want to interact with any other element because it already has that 2 electrons in its first shell and the shell is already filled. That's why it's not going to interact with anything else and it's just happy in this form. Now, it doesn't mean that helium will not be reacting with other elements or other atoms in here. It will be reacting. However, in its formal, in its natural form, it's really happy with this, setting. It really likes it when it's already having two electrons outside of its first shell. Let's talk about neon. Neon has a atomic number of 10, which means whenever we're trying to draw out the basically two shells of neon, we have the nucleus, and then we have the first shell that has two electrons, and then we have the second shell that should have a 2, 3, 4, 5, 6, 7, 8. As you can see, sorry, 8, 9, 10, there we go. Now, as you can see, the second shell of neon already has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Because it already has those 8 electrons, it's not willing to basically react with something else to make it a full shell because it's already filled. If it's already filled, it doesn't want to react with anything else. It doesn't want to have any more, electrons in here because it's really happy. It doesn't mean that neon is not going to react. It means that it will react, but it's really happy in this form. Now, let's talk about fluorine. Fluorine has an atomic number of 9, which means the number of protons is 9, and in nature, the number of protons and electrons are equal to each other. Now, the first two shell, we have 2 electrons. In the second shell, we have 3, 4, 5, 6, 7, 8, 9. Now, as you can see, fluorine has 7 electrons in its outer shell. 1, 2, 3, 4, 5, 6, 7. Now, how many electrons does fluorine need to have a full shell? And by full shell, we mean outer shell should have 8 electrons. As you can see, since it has 7 electrons, it only needs one more electron, which means whenever you see fluorine in a chemical reaction or whenever you see fluorine next to another element, fluorine only gets that one electron and that's it. It doesn't want any other electrons because that one electron will make fluorine really, really happy. And when fluorine is happy, everybody else is happy. And since we get one electron from another element, we steal one electron from another element. This means that the number of electrons are going to be more than the number of protons, because as you can see now, if we count every single electron, we get our electrons are equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons, but we have 9 protons. 9 protons. Which means if we do 9 minus 10, we get -1, which means the overall charge for fluorine, whenever we see it in a chemical reaction or whenever we see fluorine next to anything, let's say we see fluorine next to hydrogen, we should know that the charge of fluorine is -1. Because again, it wants to grab one electron in order for it to be in order for fluorine to get a full shell. Now let's talk about oxygen. Oxygen has an atomic number of, if that's 9, that should be 8. And when we write it, we're trying to draw it, we have 2 electrons in its first shell, and we have 1, 2, 4, 5, 6, 7, 8. As you can see, the outer shell of oxygen has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 6 electrons, which means if oxygen wants to have a full shell, meaning that the electrons equal to 8, it needs to get 2 more electrons from another element. It needs to basically steal 2 electrons from them. And once oxygen gets 2 those two electrons, this means that it's really happy because its outer shell has 8 electrons. Now, what does this mean? It means that the number of electrons is more than the number of protons, which means the charge, the overall charge of oxygen should be a negative number, or it should be negative. Now, protons are equal to 8, and our number of electrons, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And when we do 8 minus 10, we get negative 2, which means the overall charge is negative 2. Now, if we get the same logic and do it with every single element in here, we get negative 3 for nitrogen, negative 4 for carbon. However, some elements in this column, oh, I forgot to tell you guys that every single element in these columns have the same number of charges, meaning that fluorine, iodine, chlorine, and other elements that are in this first column, they have a negative 1 charge. Oxygen has a negative 2 charge, nitrogen, and everything else in here, negative 3. Carbon and other stuff that are here, they might have a minus charge, they might have a plus charge, but carbon is the most important one, and you need to know that carbon has a charge of negative 4, and it's always going to grab 4 more electrons from other atoms in order to basically fill up its outer shell. Now, elements in this group, they are willing to basically just lose 1 electron in order to get to a full shell, and they basically just lose 3 electrons, and that means that they take away 3 electrons, their 3 electrons go away, and they get a plus 3 charge. I wanted to explain boron because it's one of the interesting ones, and boron and every other elements in this column, again, they have the same charge, which is plus 3. Now, the way it works is when we're trying to draw it out, you have 2 electrons in here, 1, 2, 3 electrons in the second shell. And as you can see, if boron gains 5 more electrons, it can have a full shell. But since boron is kind of weak, or it's really difficult for boron to grab 3 electrons from any other atom, it's willing to lose all these 3 electrons and basically get rid of the second shell in order to have a filled shell in its first orbital. And once it gives up all those 3, it's gonna have this phase, which is basically a nucleus and first shell with 2 electrons. And this makes the charge 5 minus 2 positive 3. That's why it's a plus 3 charge. Now let's talk about every single element in the first column. We have hydrogen, and hydrogen only has 1 proton, or the atomic number for hydrogen is 1. So when we're trying to draw it out, we have a nucleus, and then we have the first shell, and it only has 1 electron. Okay, you will basically see hydrogen a lot when you're working with acids, and in every single scenario, it's going to lose that 1 electron. Once it loses that electron, basically, it's just going to be a proton, because there's nothing else in here except for protons, and we have neutrons. But since neutrons have a charge of 0, they basically don't count as a charge. They're just gonna, this hydrogen is gonna be just a plus 1 every single time. Now, since it's only going to have 1 proton and that's it, they basically, a lot of time, chemists call this a proton because it's just a hydrogen that doesn't have any electrons and it's just 1 proton. That's why they always call it a proton. Now, I know that hydrogen might be something kind of confusing, but you can watch a lot of videos about it. I want to talk about another element in this column so it can make sense to you. Now, lithium. Lithium has an atomic number of 3, which means that whenever we're trying to draw it out, we have 2 electrons in the first shell and 1 electron in the second shell. As you can see, lithium only has 1 electron in its outer shell. In order for lithium to have a full shell or a filled shell, it has to gain 7 more electrons. 7 more electrons. And as you can see, it's not something easy for lithium to do because if it gains 7 electrons, it's entirely impossible for it because it only has 1 electron and that electron is really weak. And sometimes that electron just wants to get out of that atom and it just wants to run away. Now that's why every single time when lithium is reacting with something else, it's just going to give up that 1 electron and that 1 electron is going to run away from it, which means that the outer shell or the second shell will fade away and we're just going to be left with the first shell with 2 electrons. And as you know, the first shell with 2 electrons means a full shell. It's a full shell or orbital. And when we're trying to count the amount of electrons and protons, we do 3 minus 2, and we're just going to be left with +1 or +1, which means every single element in the first column should have a +1 charge. Now, beryllium has an atomic number of 4, and the first shell has 2 electrons and the second shell has 2 more electrons. And again, if you think about it, we need 8 electrons for the second shell to be filled, and we already have 2 of it, which means we need 6 more electrons from another atom. And again, it's really difficult for beryllium to gain those 6 electrons, so that's why it's just going to leave these 2 electrons for any other atom, and it's just going to give up those 2 electrons and give up, which means that the second shell will completely fade away and we're just going to be left with 2 electrons. And if we're trying to find the charges, again, it's +2, which means the charge of every single element in this column should be +2. And you might ask, why do we do 4 minus 2? The reason is that the charge of protons is plus and the charge of electrons is -2, basically minus. So we do plus, minus, and then 4 minus 2 equals +2. And yeah, this is it. And I just want to say that every single time you see these elements with something else, like if you see beryllium oxide, you should know that beryllium is something that's going to give up 2 electrons, which means the charge of beryllium should be positive. And since we already know the shortcut, we know that it's beryllium +2 and oxygen -2. And it can be that easy, but sometimes they might get tricky. But for this video, I just want to tell you that this is how it works. And let's say another example that I wanted to do was hydrogen and fluorine. And this is hydrofluoric acid, and we will talk about it later a lot when we're doing acids. But in here, again, we have to recognize that hydrogen is in the first column, which means hydrogen should be +1, and then fluorine is in here, which means the charge of fluorine should be -1. Thank you.